This new lithium extraction method could change clean energy. Source: Columbia University School of Engineering and Applied Science Research, published in the journal Joule. If you like my videos, subscribe my channel and press the bell icon to turn notifications on so you keep getting all the major advancements in science and technology. And don't forget to like and share this video with your friends and colleagues. Comments are welcome and open for discussion. For decades, lithium has been called the white gold of the clean energy revolution. It powers electric vehicles, large-scale renewable energy storage systems, smartphones, laptops, and countless technologies, shaping the future of modern civilization. But behind the promise of clean energy lies a major hidden problem that few people ever see. Extracting lithium from the earth is often slow, environmentally damaging, and heavily dependent on enormous industrial operations that consume huge amounts of water and land. Now, scientists at Columbia Engineering may have discovered a radically cleaner and faster way to obtain this critical material, a breakthrough that could reshape the global battery industry and dramatically improve the sustainability of the clean energy transition itself. The demand for lithium is exploding at an unprecedented rate. As governments and automakers push toward electrification, millions of electric vehicles are being manufactured every year, while renewable energy systems increasingly rely on massive battery installations to stabilize power grids. Yet the world's current lithium production methods are struggling to keep up. Today, nearly 40% of global lithium comes from underground salty brines trapped beneath desert regions. In places like Chile's Atacama Desert and parts of Nevada, companies pump enormous quantities of mineral-rich brine into giant evaporation ponds that stretch across vast areas of land. The water then slowly evaporates under the sun over periods that can last months or even years, eventually leaving behind concentrated lithium salts for processing. The process works, but it comes with serious environmental costs. These evaporation ponds consume enormous quantities of water in some of the driest regions on Earth, placing additional stress on already fragile ecosystems and local communities. The technique also depends heavily on specific climate conditions, requiring intense sunlight, low humidity, and flat terrain. Many potentially valuable lithium reserves around the world simply cannot be economically extracted using existing evaporation technology. As global battery demand accelerates, scientists increasingly recognize that current methods alone may not be capable of supporting the future clean energy economy. This is where the new Columbia Engineering breakthrough becomes especially important. Instead of relying on massive evaporation ponds, the researchers developed a completely different extraction system known as switchable solvent selective extraction, or S3. The approach uses a specially engineered temperature-sensitive solvent capable of directly pulling lithium out of salty underground brines far more rapidly than traditional methods. The chemistry behind the system is remarkably elegant. At lower temperatures, the solvent absorbs lithium ions along with water molecules from the brine. When the system is heated, the solvent changes its behavior and releases purified lithium and water while regenerating itself for repeated reuse. What makes the process particularly powerful is its selectivity. Underground brines rarely contain pure lithium alone. They are typically filled with competing minerals such as sodium, potassium, and magnesium that make separation extremely difficult. Existing extraction systems often require complicated chemical processing steps, expensive binding materials, or energy-intensive purification techniques. But in laboratory testing, the S3 system demonstrated the ability to selectively extract lithium at rates up to 10 times higher than sodium and 12 times higher than potassium. The researchers also developed methods to remove magnesium contamination through targeted chemical precipitation, allowing the process to isolate lithium far more efficiently. One of the most significant aspects of the discovery is that the method works even on lower quality lithium sources that current technologies struggle to use effectively. To demonstrate this capability, the team tested the system using synthetic brines modeled after conditions at California's Salton Sea geothermal region. The Salton Sea is believed to contain one of the largest untapped lithium resources in the United States, potentially enough to support the production of more than 375 million electric vehicle batteries. Yet, the chemistry and environmental conditions there make conventional evaporation techniques impractical. The new S3 process could potentially unlock these enormous reserves using a far cleaner and more scalable approach. The researchers reported that after only 4 extraction cycles using the same batch of solvent, the system successfully recovered nearly 40% of the available lithium. Although still in the proof-of-concept stage, the results strongly suggest the technology could eventually support continuous industrial-scale operation. Even more importantly, the process can operate using relatively low-grade heat sources, including waste industrial heat or solar thermal energy. That means future lithium extraction facilities might require far less energy than conventional mining and evaporation systems. Beyond the chemistry itself, the breakthrough highlights a deeper issue surrounding the clean energy transition. Electric vehicles and renewable power systems are often described as environmentally friendly, but the mining and processing of critical materials remain major sources of pollution and ecological disruption. Lithium extraction in particular has become increasingly controversial because of its water usage, land impact, and chemical waste. Scientists involved in the project argue that creating cleaner extraction technologies is essential if the world truly wants sustainable energy infrastructure rather than simply shifting environmental damage elsewhere in the supply chain. The implications extend far beyond electric cars alone. Lithium is rapidly becoming one of the most strategically important materials on Earth because it sits at the center of global energy storage technology. Faster, cleaner, and more scalable extraction systems could help stabilize battery supply chains, reduce production costs, and support the expansion of renewable energy infrastructure worldwide. As countries compete to secure domestic sources of critical battery materials, technologies capable of extracting lithium from previously unusable brines may become economically and geopolitically transformative. Perhaps most importantly, this research demonstrates how advances in chemistry and materials science are beginning to solve some of the hidden bottlenecks limiting the clean energy revolution. Renewable energy technologies are not only about generating electricity from sunlight or wind. They also depend on enormous industrial systems capable of producing batteries and storing energy at global scale. By redesigning how critical materials like lithium are extracted, scientists are helping build a future where clean energy may become not only more efficient, but also genuinely more sustainable from the ground up. Although substantial engineering challenges remain before the technology becomes commercially deployed, the proof of concept is extremely promising. If future development succeeds, giant evaporation ponds stretching across deserts for years at a time may eventually be replaced by compact, reusable chemical systems capable of extracting lithium far faster and with far less environmental damage. In the race to build the clean energy future, scientists may have just discovered a cleaner way to obtain one of its most important ingredients.